Right, folks, we are on to the structure of the Earth, as you can clearly see. I'm just going to take the opportunity to remind you that if you do get stuck on any bits of this module, it started kind of getting a little bit more complicated in the last two videos, which were all about how do we know about plate tectonic theory and sort of the history. Nick is doing weekly question and answers on YouTube. He's keeping them to Mondays at 2 o'clock. So obviously you can send your questions to him whenever. In fact, I would send the questions as soon as they pop into your head, to be honest. And then at least you know at some point you're going to get an answer to that question. Okay, if you have a copy of the module booklet, it's pages 15 and 16. If you have printed one off at home or you're using the digital version, it says structure of the Earth at the top of the page, and there are some diagrams of sections of the Earth. Okay, without further ado. So the first question is, how on earth do we know? Because the deepest mines on Earth are 12.5 kilometres. Clearly that's not going to the very centre. So how do we know? And it's actually all because of earthquake waves. Now, I'm not going to teach those to you today. They will come up when we get to earthquakes, funnily enough. But because of the behaviour of how they travel and refraction and speed and all sorts of things, that's how we know what the structure of the Earth is. Now, there is a film opportunity here. I won't open this hyperlink. It's a trailer of a movie called The Core, and actually you could watch the whole movie if you wanted to. You do definitely have to poke holes in the science of that one, but it's quite a good disaster movie and it will pass a bit of time. This PowerPoint is still called, I think it's Intro to Module. It definitely is Intro to Hazards or Intro to Module, something like that. And it's the same PowerPoint that I've been using in all of the videos so far. Okay, so how do we know about it? Because of earthquake waves. So this is how I learned the structure of the Earth at secondary school. My teacher likened it to a Scotch egg. Whether that works for you, I'm not sure. I'm afraid our version is a little bit more complicated than that. But the first thing that we need to think about is why. Why are there different layers? Because that's quite an important idea. So I'm going to hand over to somebody else to explain this, because it's really good.
This year, I'm buying Central Park, and
management's gonna freak out.
Stop messing up my party! It's gonna be
I can't skip the ad, folks, sorry. There we are. Sorry, I couldn't skip that one. So.
Hey, I'm just making a planet. Well, this is how planets like Earth get their structure anyway, because of different layers of density. Even today, with all of our modern technology, we've only been able to drill about a third of the way through Earth's crust. So, how do we really know if it's solid, liquid, hollow? Luckily, Earth has this tendency to violently shake and occasionally burp up some of its insides. And that's taught us a lot about our planet's guts without having to go down there. We're used to seeing density at work. That's the same reason that the atmosphere, the least dense part of our planet, is on the outside. And the crust, the second least dense part of the Earth, is beneath our feet. Because I'm less dense than the dirt, I don't sink into the ground. And even though there's about 1 ton of atmosphere above my head, it's not dense enough to send me floating. The main layers of the Earth are organized in the same way. Depending on whether they're divided up by how they squish around or what they're made of, geologists give different names to the different layers of the Earth. So that's how it is now. But to really understand why the Earth is organized the way it is, we need to go back to before our planet even existed. In the very young universe, hydrogen and helium were pretty much the only elements around. They condensed into stars, began the process of nuclear fusion, and eventually died, spitting heavier elements from carbon and oxygen to things like nickel and gold back out into the universe. One of those heavy elements, iron, is the most stable element produced outside of a supernova, and the early universe produced a lot of iron. That'll be important in a second. Fresh hydrogen and helium went on to form new stars like our sun, and the heavier elements collided to form the dust and debris that would become our solar system's planets and moons and asteroids and everything else. High temperatures in the early inner solar system meant that light volatile elements could only condense further out, which is why the 4 inner planets of our solar system are dense and rocky, while outer gas giants like Saturn could hypothetically float in a really big swimming pool. After proto-Earth grew larger, radioactivity, gravity, and violent boom booms melted that messy mixture of rocks and minerals, and this is where things started to get organized. Just like that tower of density, the heaviest materials like iron and nickel worked their way to the core. The lighter materials like aluminum and silicon stayed near the surface. The inner core experiences pressures more than 3 million times what we do on Earth's surface, which means that despite being as hot as the surface of the sun, the iron in our planet's inner sphere is likely solid and not liquid. The outer core is most likely liquid because it's hot, but not under as much pressure as the inner core. We know that's the case because of earthquakes appear on the surface. As certain kinds of seismic waves travel through the Earth, the liquid outer core either refracts them or blocks them altogether. And that creates seismic shadows on the opposite side of the planet. If you want to use pressure to melt metal at home, just stack up 16 million pennies. The one on the bottom should liquefy in no time. Mercury is so close to the sun that its atmosphere has long since blown away. But luckily for you and me, our liquid metal outer core lets us have an atmosphere. Deep metallic convection currents create a magnetic field that shields Earth from the solar wind. Otherwise, we'd be pounded with deadly radiation, our atmosphere would be blown away, and Earth really wouldn't be a very lifey place. Over time, Earth continues to cool, so more and more of its liquid outer core is turning solid, and we're shrinking little by little. Every earthquake that we feel is Earth taking one step closer to cooling off and becoming a real third rock from the sun. So there you have it. Like Carl Sagan said, we are star stuff who has taken its density into its own hands. It's density, right?
Okay, so quite a lot of information in that, but what we're trying to focus on is just the difference in density. If you do physics A level, I'm sure you have to know quite a lot of that other stuff, but I just think that clip's really helpful because it links it all together and it kind of helps you make sense of the world a bit more. The only thing we really need to take from it is that the Earth has layers because the things are different densities. So the heavy stuff has sunk to the bottom and the lighter stuff is on the outside. Now, what he alluded to in that video is we have 2 ways of labelling the structure of the Earth. You've got this diagram on page 15, or the page with the structure of the Earth information on it. I've also included a slightly different version, sort of a pizza slice effect, if you like, so that you could print that off or copy that if you prefer it. What we're trying to get at is compositional means what is it made of, and mechanical is how does it move, okay? Now, I have good news for you in that, and I'll repeat this at the end of the video, you are not going to answer any short questions on tectonics. Your 3 second year modules, which are tectonics, weather and climate, and development in an African context, you will write 1 essay per module, and that's it. I know some of you are not big fans of essay writing. Don't panic, we'll get there with essays. That we've got ages to worry about those. But you cannot get any short questions for your year 2 modules, which means they can't give you a diagram of this and, you know, ask you to label it or whatever. So what we need you to do in tectonics is get the big ideas. Nitty-gritty detail is lovely for showing off and things like that, but you cannot get any 2, 3, 4, 5, all those kinds of numbers of marks. You are just going to write 1 essay. So we don't want to get too bogged down in all of the detail. Okay, but compositional, what's it made out of? Mechanical, how does it move? You will probably be quite familiar with the compositional because that's sort of the Scotch egg one, although usually you divide the core into inner and outer. Mechanical layers, so the lithosphere is the really solid bit, it's the bit we live on. If you I suppose, no, it's not a Scotch egg. If you use the analogy of an egg, it would be the egg shell. So the lithosphere is the solid bit. The asthenosphere is really quite important for plate tectonics. So you don't describe it as liquid because it isn't. You describe it as a semi-solid, or you describe it, if you're a geologist, as plastic, which might confuse some of you. The way to think of the asthenosphere is a bit like Play-Doh, blue tack. It is definitely a solid. There's no way that you would describe blue tack or Play-Doh as a liquid, but it can move. And that's really important because otherwise, where does the movement of the plates come from? If everything is solid, it just doesn't work, does it? Okay, so yeah, the asthenosphere, think of your own sort of way of describing it. Semi-solid plastic, moves like blue tack or Play-Doh, however you want to come up with a description. But that is quite an important layer for us. Meso or mesosphere is, I think it means middle actually, and that kind of makes sense, doesn't it? Because it's the bit in the middle, and then the outer and inner core that we've had explained to us. So, how do we know about them? Behaviour of earthquake waves. Why are there different layers? That's all because of different densities. But as long as you get the idea of this, you don't have to worry about learning it off by heart or anything like that. And if you find that one easier, then yeah, by all means. So you can see you've got the composition on the left and you've got the mechanical on the right hand side. It's just another option for you. All right. So for me, I think two of the most important bits on pages 15 and 16 are the discontinuities, which I'm going to explain to you now, and the differences between oceanic and continental crust. That's really, really important stuff. And I'm going to give you some suggested tasks at the end of this to try and get those really in your head. Right, first of all, Mohorovicic. Those of you that follow international football might recognise that as a Czech name, and you would be right, so congratulations. Most people do not have the enthusiasm, I don't know what the right word is, to write out Mohorovicic, so he gets shortened to Moho, perhaps slightly disrespectfully, but anyway, the Moho, the Gutenberg and the Lehmann discontinuity. They're labelled on the diagram on the screen, which you also have on page 16, and you might want to just do a little bit of labelling. So, discontinuity is where something stops being continuous. So discontinuity is the opposite of continuity, which is keeping something going. What we mean by a discontinuity is it's where the earthquake waves, seismic waves is just another name for earthquake waves, it's where your earthquake waves change speed. So it's these discontinuities that helped us figure out the structure of the earth, and that's why they're quite important. So Moho, he was a Czech scientist. Lehmann, I think she was Ingrid Lehmann, she was a female anyway. So there are 3 points, if you like, where we know that the structure of the earth changes because earthquake waves change their behaviour. Do you need to learn all of their names? Again, remember, you can't be asked short questions. It would be lovely if you can, but at probably the very least, what would be lovely is if you were able to like drop in the name of one of the discontinuities into an essay and use that as a little bit of extra detail. But then I said the other thing, and I would argue this is probably the most important bit about the structure of the Earth, the differences between oceanic and continental crust. This one you can see, this is a contour map basically, it's a crustal thickness map. Perhaps unsurprisingly, the Himalayas are the thickest bit of crust because they are being created by a collision margin. We're going to be moving on to margins for the rest of this week. So you've got two bits of continental crust crashing into each other, and as they crash into each other, they crumple up a bit like a car bonnet does in an accident. So they crumple up and the crust gets thicker and thicker. But you can see some mountain ranges quite clearly shown. All of the oceans, the crust is much thinner, and what this is beginning to tell us is that there's already one significant difference between oceanic and continental crust. Here is a slightly different way of showing that. So on page 15 and 16 there's some text which begins to talk to you about the different characteristics of these. This is really, really, really important, and there's a little bit more information. I'm not going to show this one because, as you can see, it's 6 minutes, and I'm not going to show you that within my video. But you can also see on the right hand side in the menu, there is quite a lot on YouTube about the structure of the Earth. So if this topic is a little bit trickier for you, you've got plenty of stuff to choose from. So get your head around the differences. So just firstly, you can see the oceanic crust is much thinner than continental. Well, continental crust cannot be created or destroyed. It was created at the beginning of the history of the Earth, and it cannot be destroyed because it is so much less dense than oceanic crust. It would be like trying to make a cork sink in a cup of water. It's never going to happen. So continental crust cannot be created and it cannot be destroyed, but it moves around the planet. We talked about continental drift. So as the plates move 5 to 10 centimetres a year, the continents are sort of like on a raft, if you like, and the continents move around and they crash into each other, and because they cannot sink, they just get crumpled, and it's called fold mountains. So the continental crust generally just gets thicker and thicker. Oceanic crust is continually created and destroyed. So it's created at what you probably call constructive plate margins, and we're going to be talking about those more this week. And it gets destroyed in destructive plate margins. So oceanic crust is much younger because it's constantly created and destroyed, and it's much thinner. So you can begin to see that there are quite a few differences between those two types of crust that are, in my opinion, as I've said, the most important learning point to take from this bit of the syllabus. So what I'm suggesting is, as a result of this video, you might want to create yourself a bit of a glossary to help you learn what the asthenosphere is. You might want to have discontinuity in there, that sort of thing. So there's quite a few new words that it might be worth sort of working on. I like a table, but you might be more of a spider diagram or other options. Create yourself some kind of differences on the continental oceanic crust notes. Make sure you know why there are discontinuities. Maybe check out some other YouTube videos if that's causing you a little bit of stress. But as I've said, remember, you can't get any short answer questions, so we don't need to get too bogged down in teeny little bits of detail, unless, of course, that teeny little bit of detail is the thing that's preventing your brain from understanding it, in which case send Nick a question for his question and answer sessions, because you don't want that tiny little detail to stand between you and kind of understanding what it is that you need to. All right, so what we're going to be moving on to for the rest of the videos this week is we're going to talk about plate margins. And it may well be that by the time we get to the end of all of those plate margins, you're actually a little bit happier with some of the difference between continental, oceanic, crust, etc., etc. I sort of feel with tectonics that the first few lessons, I'm sort of giving you pieces of a jigsaw puzzle, and it takes a couple of weeks to see what picture it is you're creating, if that analogy makes sense. So yeah, it might be that you just need a few more videos for that to sink in. Okay, see you in the next one.